Reviewing. What is a definite integral? I'd like to cover that. What is a definite integral?
Specific spots on the.
Yeah, it nails down specific spots where you're actually finding the area from left to right. That's what the A to B means. And then what's the answer from it?
An area.
Yeah, an actual area, a single numerical answer. Okay, and then what is an indefinite integral? Done it?
Just the formula?
Yeah, it's just formula. It's the antiderivative formula, which, if you think about it, if you're thinking that, say, let's say f of x is actually the function itself, so that's the y value, and then f prime represents the slopes, and f double prime represents the concavity. Another thing we could do is go back to physics and say, this one represents the position of a particle over time, and this one represents the velocity of the particle over time, and this one represents the acceleration of the particle over time. Then we can basically move back and forth between these formulas by taking derivatives and antiderivatives. So if you move downward, you're taking a derivative. And you move downward, you're taking a derivative. And when you move downward, the answer is unique. You take the derivative, there's one and only one answer. Whereas if you want to move upward, say from acceleration up to velocity, you take an antiderivative, and the only trouble there is that it's not unique. There's a plus c at the end. So there's actually not just one formula that you get, but rather infinitely many formulas depending on the value that you plug in for c. And likewise, if you move up again, you're taking the antiderivative. And again, when you take that antiderivative, you're putting a plus c at the end of it, so there's infinitely many choices. So just imagine if you start at acceleration and do the antiderivative once, there's a plus c at the end. But then you do the antiderivative again, there's another plus c at the end. Let me just consider. Here, let's say that our acceleration, of a particle was modeled by the simple formula 9.8, which is our own acceleration here on Earth, 9.8 meters per second squared. That's the acceleration of an object near the Earth. So if I take the antiderivative, the first thing I'd come up with is that the velocity would be 9.8t plus c. And then if I want to take the antiderivative again, well then I would have the position of the particle, which would be t to the power of 2, so add 1, and then divide by 2. And then c would become ct, and then plus a whole new c. And so there's quite a bit of flexibility there. You've got one particular c value there, which is determining the velocity of that, or the position, and another c value determining the original y-intercept. Okay, not that we really need to know all of that. I just wanted to share that we have these three formulas that we play in, the original, the derivative, and the second derivative. And that if you move downward, you're taking unique derivatives. If you move upward, taking integrals, you get a plus c at the end, which is a flexible formula that can take one of infinitely many values. And that's kind of where we're playing right here. Right? This is our space of playing, is moving back and forth between these functions by taking derivatives and integrals. Okay, next, what's the verbalization of the power rule? So let's say that you had f of x equals x to the n. How would you describe verbally to someone the derivative? Someone who hasn't spoken yet. How do you take the derivative? You multiply by n, and then? What?
Plus 1 and then
Which?
plus 1. No, minus 1.
Yeah, minus 1. Yeah, so the derivative is to multiply and subtract, whereas let's say I wanted to take the integral of x to the n. Thank you, Colleen. What's that rule? How do you do the antiderivative of x to the n, Sarah? You add 1 and then divide by 2. Yeah. So, well worth writing that down somewhere, like tattooing it on your hand maybe, because these are so easy to mix, right? Thank you for demonstrating how easy it is to mix those up, It's very easy to mix those up. Okay, all right, so that's it. All right, so we've covered a lot of ground in taking derivatives and antiderivatives. And what we're going to talk about today is how to take more integrals. So I want you to notice that we have a fairly limited capacity right now for taking an integral. These are the things we can integrate. We can integrate a power function, like x to the 4th. We can take that integral. We can integrate e to the x, because it's just d to the x. We can integrate 1 over x, because that would be the natural log, and that would just be e to the x, and that would be x to the fifth, 1 over 5. So what you notice here is that we really only have the ability to take the integral of simple, single functions. But recall, when we were developing the derivative, we didn't just want to be able to take the derivative of something simple, like x to the fourth. We wanted to be able to take the derivative of something complex, like a product, x to the fourth times e to the 2x. And so we had a product rule. And we also wanted to take the derivative of a quotient, so like e to the 2x over x to the fourth. And so we had a quotient rule. And we also wanted to be able to take the derivative of a composite function. I suppose that'd be a good description of it. So something like the square root of x squared plus 2, because that's really the derivative of x squared plus 2 to the power of 1/2. And so we had an inside function and an outside function, and so we had a chain rule. And so now we're left with the same desire. You know, how do we take the integral of a product? Right? How would we go about doing that? Or how would we go about doing the integral of some sort of composite function? How would we go about doing that? And all we really need to do is know how to do a product and a composite. Because if you think about it, a quotient rule is really just something extra we don't even need. Because can I take e to the 2x over x to the fourth and rewrite it as not a quotient? Yeah, I mean, I can just bump that x to the fourth up to the top. And it'd be e to the 2x times x to the negative fourth. And that kind of poor, sad quotient rule is really completely unnecessary. We don't even need to study quotient rules because a quotient is really just a product in disguise. Sad quotients. Does that mean that fractions don't exist? Like, what if I took the fraction 2/3? Could I rewrite that as not a fraction? I mean, couldn't I write it as a product of 2 times 3 inverse or 3 reciprocal? I suppose we could. Yeah, we could just do away with fractions completely. Who would like to write a fraction like that? Maybe not. You know, I think we're all pretty used to writing down fractions like this, and it almost makes intuitive sense. I have 2 slices out of 3 slices of pizza. Like, it's pretty intuitive to us now. We probably wouldn't want to embrace a system like that. So, in any case, this is where we're headed. We still need a product rule of sorts, and we still need a chain rule of sorts. But keep in mind, what we really want to do is how to take the antiderivative of a product and the antiderivative of a chain rule. Kind of like to undo the chain rule and to undo the product rule. That's what we're really saying, is how do I undo a product rule and how do I undo a chain rule? Because when we do an integral, we're doing an antiderivative, which means the antiderivative of a chain rule that's already done and the antiderivative of a product rule that's already done. So we're really just trying to work backwards. Okay, well, that's where we're heading in the remainder of chapter 3. Anyone, you want to ask any questions? Yeah, Henry.
How come we did it for
So you can say howdy hi outside ho 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 ho. No, why? Because I mean that's a really good point. I mean, why bother learning an extra rule when you can just take any quotient and just turn it into a yeah? Can anyone think of a good reason why we learn quotient?
that when we did it?
Yeah. Yeah, I mean, what would be an example of a quotient rule that we would have done? So like maybe x squared plus 3x over, let's say, the natural log of x. So that's a quotient. Is there any benefit to doing the quotient rule versus the product rule? So I could just rewrite this as x squared plus 3x, but then I would have to write natural log of x as natural log of x to the negative 1. So I think we could just do the product rule like that. There'd be no reason why not to. Yeah, I suppose it's to each his own, Henry. If you would like to, starting now, never do the quotient rule again, you could. You'd be like, whatever, quotient rule, I'm not messing with you. All right. Anyone else, thoughts or questions? Is that a very bad thing? I thought it just meant like, I spit on you. Is it worse than that? Maybe I should do the whole like, is it you bite your thumb at someone in Shakespeare? Or you thumb your nose at someone? I don't know. I didn't mean to be vulgar. I'm sorry. I thought I was just being silly. All right. So here we are. It's April 4th. We're doing section 3, 4, 5, 6. I've got some padding in here to give us 2 days for 6 and 7. And we'll take a test. And then I gave us a lot of padding to do a final review day where we actually have 2 days for final review. That's amazing. I mean, we could spend 1 whole day reviewing derivatives and 1 whole day reviewing integrals. And I have a practice final exam for you. So we can spend that whole day doing those practice problems. And then our final exam is in the same room, not quite the same time. Oddly enough, our class starts at 11. I think the final exam starts at 10:30. I'll send out an email reminder about that when we get a little closer to May. All right. Did I already tell you the surrealists? No. I did? Oh, Josh, you poor man, you weren't here. Did I do the knock-knock? Oh, darn it, I did them both. Well, Josh, you can get to hear them. How many surrealists does it take to screw in a light bulb? A fish. That's one joke. Well, that's fine. No one gets the surrealists either. No, you know who surrealists are? Like Salvador Dali with his weird pictures of like, here, I want everybody to see it. Because then, if you remember who a surrealist is, then the joke is funnier, and then you'll want to go home and tell it to your friends and family. So, surrealism, Salvador Dali. Salvador Dali, I think, was the founder of the movement. That's surrealism. You know, the things don't really make too much sense. But that's kind of the classic picture right there of the blocks on there. Yeah, they're all kind of strange. All right. What do we need here?
So now the joke makes sense.
You what, Josh?
So now the joke makes sense.
There you go. That makes sense. Another one related. What do you call a fish without an eye? All right. Good one, Sarah. That was nice. I couldn't have paid you to laugh that long. All right. So section 3.4, what we're going to talk about is substitution and integrals. And what we're really doing today is doing the chain rule in reverse. This is the packet for today. And yeah, see me in the break and I'll give you the ones from previous. So if we wanted to do the chain rule in reverse, we might as well go ahead and start by just doing a chain rule and then seeing how you would go that and do that backwards. So let's just think of a classic chain rule. I'm going to take the derivative, and everyone do this with me. I did give you space up at the top to take some notes. So maybe just do this kind of small because this isn't even the notes I want you to take yet. But if we did take the derivative of a chain rule, so let's say that we do something interesting enough, 3x squared plus 5x, all raised to the power of 8. There, that'll be our chain rule. So it's been a while since we've done the chain rules group. Recall, you have an inside function and an outside function. Do you see the inside function? And do you see the outside function? Okay, let's review the steps of the chain rule. When you do the chain rule, you take the derivative of the outside. So that'd be 8 to the 7. Right, bring down the 8, subtract 1. Take the derivative of the outside, do what to the inside? Leave it alone. And then multiply by the derivative of the inside, which would be 6x plus 5. Okay, so that's just a basic chain rule there. Let's look at this for a moment and see what we see in here. See what we see. Let's see what we see, folks. So first of all, there's a couple things. First, hopefully, you still recognize that outside function which has been taken the derivative of. Right? So just kind of looking there, if you saw just walking down the street, if you saw walking down the street, you saw that somewhere, you'd be like, hey, that looks like something that had been taken the derivative of. Right? Because you bring down the 8 and subtract 1. So maybe there'd be some visual recognition there. Likewise, somebody give me another one. What's something that would have had been taken the derivative of? Just another example.
Something to the same.
To the 7th? No, I don't think so. Not the 7th, to the 5th. Yeah, there you go. Yeah, so there we go. There's another something which had been taken the derivative of. Okay, so that's one thing, is just kind of allowing our eyes to kind of just flexibly look at a structure and say, hey, 8 something to the 7th, that looks like that was taken the derivative of. And then furthermore, let's take a look at these two things. I've got this, that kind of piece right there, and then I look over here and I say, hey, that's the derivative of that. Right? So again, you're just kind of walking down the street and you're looking and you're like, hey, look, there's 7x cubed plus 8x. And then over there, you're like, hey, wait a minute, that's 21x squared plus 8. Hey, well, hey, that's the derivative of that. Right? So these are just things that you would just kind of visually pick out if you allowed yourself a moment to look and see the relationship. What's that? Oh, okay, that makes sense. Okay, so we're just allowing ourselves to notice these things. So then if you notice all of that simultaneously, and you're like, hey, this is an outside function that was taking the derivative of, and then this is the derivative of this whole thing is the chain rule, right? That's very different from doing the chain rule. Like previously, we just worked on doing the chain rule, which is take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. But now we're actually looking at this saying, okay, I see this outside function, and that's definitely the derivative of a previous outside function. And I see that this is the derivative of this. And by noticing that and looking at that, you'd say, I think this thing is the result of the chain rule. Right? This thing that I'm looking at here, I think that's the result of the chain rule. So let me give you one, okay? Let's say that you're walking down the street and you see this. Is that the result of the chain rule? I didn't ask you to do the chain rule. I'm just saying, hey, take a look at that thing. Is that the result of the chain rule? You kind of checked out every part and piece. You're like, oh yeah, that checks out. Okay, yeah, that checks out. Okay, correct. That one is the result of chain rule. But now let's say you're walking down the street and you saw this. Is that the result of the chain rule? No. Where did it break down? Yeah, there's that 2 there. This thing is not the derivative of this. So you'd say, no, this thing is just some cobbled together gobbledygook. You know, it's just like something, but it's not quite the result of the chain rule. Likewise, if maybe you had this, and then you had this, is that thing the result of the chain rule? Yeah, I mean, at face value, no. Right? Because you're like, well, that doesn't really make sense, because that would have been bring down the 7, subtract 1. Well, but is this still the derivative of this? Yeah. Now let's focus on that for a minute. This is still the derivative of this, which is pretty critical. It's almost more critical than this, because watch, I'm going to do some trickery, because the subtitle of the class is Advanced Techniques for Algebraic Manipulation and Subterfuge. And so what if I rewrote the number 5? Instead of the number 5, I'm going to write it as 5/7 times 7. Am I allowed to do that first of all? Can I rewrite the number 5 as 5/7 times 7? I'm allowed to. And now is this thing the result of the chain rule?
Yeah.
It sure is, because I brought down the 7, subtracted 1. That's the derivative of that. And there just happened to be a coefficient out front. Right? So how important is that the coefficient is correct? Yeah, I mean, that could be -2 for all I know. And would this still be the result of the chain rule? Yeah, that thing is still the result of the chain rule. So what really matters? What really matters for us to see that something was the result of the chain rule? Yeah, that part. If you're going to see something that's the result of the chain rule, you better see something that was the derivative of something else, and that something else was the inside function of an outside function. So what really matters that I can claim that something was a chain rule would be this. Now I just wrote that in a very formulaic way. But now do we still see? We have the derivative of the inside function. There was some sort of outside function, and there's some sort of constant out front. And that's all that really matters. That's all we really need to see in terms of recognizing that something was the chain rule. That maybe that was a little too formulaic to write it like that. But even this, would you agree that this is still the result of a chain rule here? Potentially? Just potentially, right? Because I've got a function as an inside function of some sort of outside function. Sitting outside of it is the derivative of itself. And then there may or may not be some coefficient out front for those. Okay, so we now have at least the willingness and ability to consider whether or not something was the result of the chain rule and whether or not it was not the result of the chain rule. So for instance, what if I had this? Is that the result of the chain rule? Why not? Yeah, there was no derivative of something else also present in the formula. So for there to be a chain rule, remember, you always have to take the derivative of the inside function and plop it outside. And this one, there's an inside function, an outside function, but there was nothing outside. There was the derivative of the inside. So what are we really looking for when we look for something that was the result of a chain rule? You have to see something, 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 a function, and then something, 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 the derivative of that function. And that's really what you're looking for the hallmark. If you have some mathematical expression, and somewhere in there you see a function, and somewhere else you see the derivative of that function, you say, whoa, this thing could be the result of the chain rule. Is that fair? Does everyone feel okay about that? That's what we're really looking for? Okay. All right. Well, this just to kind of get us in the mood. So let's talk about the chain rule real quick. Let's say we actually do the chain rule. So everyone now write this down for sure. So d dx of f of g of x. We're going to do the chain rule in reverse. So first, let's do the chain rule forward. Make sure you have this in your notes because it's been a while. So we take the derivative, and how does it work again? We do the derivative of the outside, leaving the inside alone, and then we multiply by the root of the inside. So that is the chain rule. And if that's the derivative, then whatever result you get from a derivative, I can now take that thing and integrate it. So the integral of f prime of g of x times f prime of x dx, what will that integral equal? Yeah, just the original, f of g of x. Plus c. All right, so this again is just kind of a visual recognition that if you did do the integral of a chain rule, you would just get a composite function back out. Josh.
You put it as prime of j of x times prime.
Oops, I did. Thank you. Josh, I did that on purpose to see if anyone would catch it. We did, so thank you for that. All right. Well, that's what we're looking for. So now let us go ahead and try one. I have to admit, it's a little awkward at first, so the main thing I suggest you do is definitely write down everything I write down, and then we'll do a couple of these to see how it works. Now, the main thing, notice, okay, when we're integrating something that was a chain rule, what are we integrating? A product, exactly right. That's what we're kind of hoping for. So what we're saying now, leading into this section 3.4, is that we are able to take the integral of certain products that were the result of a previous chain rule. So not every product. You know, right now, like if I gave you the product 3x squared plus 4x times e to the x, that is a product, but that product is not the result of the chain rule. So right now we would just be stuck. We wouldn't have a way to solve this thing. Okay? So right now what we're saying is that we are able to solve certain integrals of certain products provided that product was the result of the chain rule. And that's what we're going to practice today. That might seem like really like a niche thing, right? Like today we're going to learn how to take the integral of products, but just certain products sometimes on the weekends, right? It's got to be certain very special products, but that is what we're saying. Okay, this was just previously all the rules that we had, and the goal, we're not even going to look at this right now. Let's just go ahead and try one. So is this what you're looking at? Okay, so you already kind of filled in some notes up at the top. And so what we're going to do is something called U substitution. Yeah, to use U substitution, you need to identify an inner function and an outer function. Consider the chain rule. Okay, U substitution, just so you know, you have done U substitution in the past. Let's just do an example real quick of U substitution. So let's say that you had, what would I like to do for my U substitution? I just want to do a here's just a very simple one, okay? Let's say that you had x to the fourth minus 8x squared plus 15. And I said to factor that. Well, first of all, I think you'd all be very comfortable factoring this. How would you factor that one? You just say, what do you multiply to make 15 that adds to make -8? So what is it? Yeah, -5 and -3. And you just factor that and you get up, right? However, I just threw a loop into this by making it x to the 4th minus 8x squared plus 15. So how do we factor this?
You substitute the x4 for a u2, and then
Yeah.
use that one for just a regular u.
Right, we are going to do a u substitution. And what we can say is, boy, I really wish this was x squared, and I really wish that was just x. Or better yet, I wish that was a variable squared, and I wish that was just a variable, because then I could just factor like normal. And so what we do is we say, well, if I let u equal x squared, let's see where that gets me. This is called u substitution. So I'm going to go ahead and put a u right there. And notice that it's a cursive u. It's actually the Greek letter mu. So it's called u substitution, even though it's the Greek letter mu, but we say u substitution. Okay, so that's me. So then what would x to the 4th be? It's just u squared, right? If I square both of those, then u squared is equal to x to the 4th. So now I call that u squared. And now I'm back to something that looks familiar to me. Very normal. I say, okay, u minus 3 and u minus 5. And now that thing is factored. Now, u substitution is a two-step process. First, you substitute in the u, and then you have to substitute out the u. So now that I'm to here, now I go back and I say that's actually x squared minus 3, and that's actually x squared minus 5. Now, you probably could have just factored this directly by saying to yourself, oh, yeah, I mean, that would have to be an x squared because x squared times x squared is x to the 4th. And since those are x squared terms, that would be an x squared term. So maybe you could have just reasoned it out. But u substitution is a nice tool that takes away that, that thinking that could hurt you. And you just do the u substitution instead. Of course, now you have to finish factoring these. And this is not a difference of squares, because 3 is not a square number and 5 is not a square number. But I don't know if I showed you this trick. But in advanced techniques for substitution and algebraic manipulation, you can call that x plus root 3, x minus root 3. And then that'd be x plus root 5 and x minus root 5. Did we ever do the Did we ever do the difference of non-squares rule? If it's not a square, you can just put in root 3 and root 3. Does that work? Can you factor x squared minus 3 into x plus root 3, x minus root 3? Does it work? Because I think we all know that if you had x squared minus 4, you can just do x minus 2, x plus 2. But the real rule, that maybe you've never seen, is that it's actually x minus root 4, x plus root 4. That's the real rule. And it just so happens that root 4 simplifies to 2. So we all just get used to saying 2 and 2, only if 4 is a square number. But even if that is not a square number, you can use the real rule, which is that. Okay, so in any case, this thing is now completely factored. You could do this zero product rule and get all of your solutions. But the key thing is you just tried u substitution. So here's what we're going to do. We're going to look at a integral. And the u substitution that you always do is you look for the inside function, and you make that equal u. So we're starting the problem now. Let u equal the inside function. You let u equal the inside function. This is the whole technique. If you can identify the inside function and let u equal that, then the rest of the technique flows. So does everyone see the inside function? What is it? Yeah, x to the power of 6 minus 7. So we're going to go ahead and say, let u equal x to the 6 minus 7. And then recall, when you do a chain rule, maybe I should still have that written here. When you do a chain rule, f of g of x, you end up doing the derivative of the outside, leave the inside alone, which is the inside function, right? That's my inside, which is my u. And that's still my inside, which is still u. But then you multiply by the derivative of the inside, which would be u prime. Or instead of calling it u prime, you can also call it du, which is what we're going to do. U prime and du mean the same thing on both derivatives. So now that we wrote down u equals x to the 6 minus 7, immediately now go ahead and take the derivative of u, because that would be what the chain rule would have you do. So now let's write du equals, and here's some formalism that we haven't done yet. So the derivative of x to the 6 is 6x to the 5th. And whenever you take the derivative of a variable now, you immediately write dx right after it. And then the minus 7, that's just 0. So there we have it. Let me say one more thing about that. When we're dealing with letters now, like we're not looking at a function per se, we're just looking at letters. There's no f of x notation here. Anytime you take the derivative of a letter, you just write du. If I was to now, starting now, moving forward, if you have a variable like y, the derivative of y, you write dy. If you had z, the derivative of z is dz. It's just a different notation. Previously, we were saying the derivative of f is f prime of x. But that's because it was a function. If we're just looking at letters and we're saying that the letters represent a function, then the derivative of a letter, well, what the letters are there? X, Y, Z. Yeah, the derivative of a letter would just be dx. So here, the derivative of u is du, and now here the derivative of x to the 6 would become 6x to the 6 dx. There's one more way to think about that, which is if x to the 6 is the function, consider the outside function 6, and the inside function is x itself. So the chain rule would say, take the derivative of the outside, which would become 6x to the 5th, leave the inside alone, and then multiply by the derivative of the inside, and the derivative of the inside is the derivative of x, which is the x. So in any case, when you write down the original u substitution, you then take the derivative, and instead of u, you write du, and you take the derivative, and at the end of it, you put a dx. Okay. Again, I know I'm springing this on you. This is the first time you've heard it. It might seem arbitrary or weird at first, but these are our steps. Okay. So what we just did right here is kind of the real work that we just did for this problem. Now it's just a matter of substitution, and the integral flows very naturally. So let's go ahead and write down now the integral in your own writing, x to the 5th, x to the 6th minus 7, 47 dx. Oh, I'm sorry, I forgot one thing. I'm so sorry, folks. Whenever you would do the derivative, if there's a coefficient out front, I want us to move that coefficient over to the other side. So a 6 over here, you divide it over to the other side, and it would become 1/6 du equals x to the 5th dx. Sorry, we're always going to do that. Whenever you take the derivative, if you end up with a coefficient out front, you immediately throw that coefficient to the other side. If you wanted to see that in more steps, so we have the du equals 6x to the 5th dx. You can either multiply both sides times 1/6, and then it's immediately obvious why there's a 1/6 over there. Or if you divided both sides by 6, you would have ended up with du over 6, which is a little awkward. So instead of writing that, it'd be 1 du over 6, which is really 1/6 du. Either way, we're just going to throw that coefficient over to the other side. Okay, so now we're ready. We're ready to do our u substitution in our integral. So let's look around and see what we have. Here's x to the 6th minus 7, the original inside function that we called u. So let's go ahead and call that u. So instead of x to the 6th minus 7, we just write u. Now, next, notice the other two bits we have. The other two bits sitting out there are an x to the 5th and a dx. And I now have an expression x to the 5th dx. And I can replace x to the 5th and dx with 1/6 and du. And I like to replace them exactly like I see them. Instead of x to the 5th, I'm going to put 1/6, and instead of dx, I'm going to put du. So right below the x to the 5th, I'm going to put my 1/6. And right below my dx, I'm going to put my du. Does everyone see that piece by piece substitution and how I did that? Because I'm relating the x to the 5th with the 1/6 and the dx with the du. So the dx becomes the du, and the x to the 5th becomes the 1/6. Okay, what's the one piece that we still have to write up here? Yeah, the power of 47. Okay. What we just did right there is called u substitution. So I just did u substitution. I like to do a step of cleanup. So let's do a step of cleanup. I'm just going to pull the 1/6 outside, and I'm really taking the integral of u to the 47. So that was cleanup. Now really look at what just happened, folks. This is amazing. Look at that original integral. Look how nasty it looks. You got an x to the 5th out there being producted with an inside x to the 6 minus 7 with a power of 47. I mean, we have no ability to do that integral. Based on what we knew so far, all we could do was an integral of a simple power rule, a simple e to the x, or 1 over x. That's all we knew. So this thing is really quite nasty. But now, by doing this u substitution, what are we taking the integral of? We're just taking the integral of a power function now. And now we fall back on the ability to know how to do the integral. It's basically magic, right? We just magically, not even calculus, magically change this integral that we couldn't do into an integral that we can do, quite simply. So now run the antiderivative. I think I'll just keep working down since I'm already working down. So the antiderivative, you add 1, divide by what you get. And don't forget to drop that 1/6 out front. The integral is now done. We're ready to see. Now, folks, I know that in the past I was working sideways. Today I'm working down. I find u substitutions work better for me if I work down. If you want to work sideways, you can. I think down works better. Plus, now you're just getting a little diversity. We've already solved a bunch sideways. Now we'll solve some vertically. Okay, so now what do? I've got 1/6, 1/48. Definitely, I can go ahead and multiply those. So 6 times 48 is the 288. So u to the 48 plus c. Now remember, once you do a u substitution, when you're all done, you substitute back out again. So our final answer would be 1/288, parenthesis, going back to what u was. What was u? X to the 6 minus 7? 48. Let's see. And that's our answer. So that was very impressive. We just did an integral of a product, and not just any old product. One of the terms was actually raised to the 47th power, and one was raised to the 5th power. That was a very advanced integral that we had no previous knowledge of how to solve, and we accomplished the whole thing by doing u substitution. And u substitution, now that you see it, doesn't really look like the chain rule or the reverse chain rule. The fact is that it is.
So, on like the inside function,
Yeah.
take the derivative
Mm-hmm.
then you move 6 to the other side by dividing 6.
Yeah.
And what happens to the x to the 5th dx? Or you're just saying that when x times x to the 5th times dx equals the same thing as
160 u. Yeah, they are literally equal to each other. They are equal to each other. They have the same value. And so I was able to simultaneously take out the x to the 5th dx and put in 160 u. Yeah. Okay, now folks, we talked about this before. Anytime you finish doing an integral, you'd look at that and you'd wonder to yourself, is it right? You know, are we right? I mean, we just did a whole bunch of stuff, but did we do it correctly? How do we check if that's the right answer? You do what? Yeah, you do the derivative, right? Because derivatives and integrals cancel each other out. So if I take this expression and I do the integral to it, and now I take that expression and I do the derivative to it, I should get back the exact same original expression. So now everybody, let's check. Let's check. The important part is to check. Let's take the derivative, d dx, of 1/288 x to the 6 minus 7 to the 48. We're going to take the derivative of that using the chain rule. So by chain rule, we take the derivative of the outside. So that means bring out the 48 over the 288, leave the inside alone, and subtract 1. And then what do we multiply by? The derivative of the inside, which is 6x to the 5th. So there's the chain rule of the answer we just got. Does that look like the original? Yeah, not quite yet. It has a lot of pieces. It has the x to the 6 minus 7 to the 47th. It has an x to the 5th. But we need to combine all these coefficients and see what we get. So what's 6 times 48, 288? That's 6 over 1 times 48 over 288. That's actually 288 over 288. Do it on the calculator, so you believe me. X to the 6 minus 7 to the 47 times x to the 5th. And that, of course, is just 1. And if I just put this in front, I get x to the 5th, x to the 6 minus 7 to the 47. And is that the original expression? Yeah. Yeah. So, as a rule, anytime you take the integral and then you get an answer, you should immediately take the derivative of it and make sure that you get back to the original. That closes the loop. That gives you great confidence that you're correct. Of course, you could be making mistakes in both directions and still get back to the original. And you're like, hey, I did it right. Right, so it's not 100% confidence that you're correct, but I would give it at least 98% confidence that you're correct by taking the integral and then doing the derivative and check that you get back to the original. Okay, well, folks, that's called U substitution. It allows us to solve certain products. Which products? Products that are the result of the chain rule. So indeed, this expression right here is the result of a previously existing chain rule. The previously existing chain rule of what function? This function. So this function, if you do the chain rule of it, you get this. And therefore, we're able to integrate it because it was the result of a chain rule. Okay, well, that was one example. Let's go ahead and do another one. And we're going to always visually inspect the product to see if it even makes sense to use U substitution. And we have a quick and simple rule for checking if U substitution applies, because we know it has to be the result of a chain rule. So we look at this thing. Let's look at it first. So this is x to the 4th e to the x to the 5th. So just looking at this, do you see an outside function and an inside function? And let's just talk about what some outside functions are. An outside function would certainly be something to the 5th. An outside function would certainly be a square root. And an outside function would also be e to the something. These are all examples of outside functions. And I know that they're all examples of outside functions because what can I do? I can put something inside them. And therefore, they are outside functions because I can put something inside them. Okay, so all of those are outside functions. Do you see an outside function? What is it? Yeah, e to the x 5th. So I'm going to rewrite this now. E to the something, that's my outside function. And what's inside it? X to the 5th. So that's step one. If you want to be able to use, so first of all, it's a product. We say to ourselves, okay, is this the kind of product I can take the integral of? Only if it's the result of the chain rule. So let's look first. Do I see an outside function? Yes. Do I see the inside function? Yes. And is the derivative of the inside function present outside? Well, what's the derivative of x to the 5th? The derivative of x to the 5th is 5x to the 4th. All we're really looking for is the non-coefficient part. Because the coefficient part, the coefficient is pretty immaterial. We can rewrite coefficients to magically appear and disappear. But is the x to the 4th part there? Yes. So we have it. We have something. I'll even draw a little arrow here. By looking at that product, we say to ourselves, is that the kind of product I can take the integral of? Only if it's the result of a chain rule. And so we say, is there an outside function? Yes. Is there an inside function? Yes. And is the derivative of the inside function present up to not including the coefficient? And the answer to all those questions was yes. So this is a candidate for U substitution. Now, do you really need to go through that whole rigmarole to say, yes, this is a candidate for U substitution? No, you don't really have to. All you really have to do is say, find the inside function. Where's the inside function? Which one of those things is the inside function? X to the front. Yeah, X to the 5th. So if you just wanted to kind of like go at it like a pinata, just be like, all right, I'm just going to find the inside function and try U substitution, see if it works. Right? So the inside function is x to the 5th, so u equals x to the 5th. So once again, you take the derivative, so that'd be du 5x to the 4th dx. So the derivative of u is du, the derivative of x to the 5th is 5x to the 4th dx. And what are we going to do with the coefficient 5? Move it over to the other side. So now I have 1/5 du equals x to the 4th dx. Okay, so now we do the substitution. So we're going to substitute a whole bunch of things. First of all, the outside function always remains. Like you'll recall in the previous problem, what was the outside function? Something to the 47. So that stayed there. That structure. the structure of the outside function stays. And so the structure of e to the stays. And so what do we put instead of x to the fifth? U. And what do we put instead of x to the fourth dx? 1/5 du. And I'll put the 1/5 below the x to the fourth, and I'll put the du below the dx. So we're swapping out as a pair. X to the fourth dx comes out, 1/5 du goes in. Now the 1/5, you don't have to bring coefficients outside the integral. I like to. I think it makes it a little cleaner, because then look at the integral you're left with. And notice that the integral that we're left with after u substitution is an integral that we know from our simple integral list, right? Once again, we have reduced a complex integral, a complex product integral, into a simple integral. So now I'm going to start working sideways because I ran out of space. So the 1/5 stays, and what's the integral of e to the u? E to the u plus c. So now that I'm all done, I substitute back for u. So now what I have is 1/5 e to the x to the fifth plus c. That's it. So I claim that's the integral. Why do I say I claim? Because I haven't checked it. I have no idea. I could have made lots of mistakes. I could have been half asleep. I could have been thinking about something else, like food. Right? Okay, so now I'm going to take the derivative to check. Check. So the derivative of 1/5 e to the x to the fifth. Remember, a constant just comes along for the ride. So it's going to be 1/5. So this is a chain rule, because I have an outside function, the e, and the inside function, x to the fifth. So chain rule says, take the derivative of the outside, and e to the anything is just e to the anything. Leave the inside alone, times the derivative of the inside. So is that the same? The 5 and the 1/5 multiplied equal 1. That leaves me with e x to the fifth with an x to the fourth. And if I just switch and put the x to the fourth out front, is that the original integral? Yeah. Just another word to the whole advanced techniques for algebraic substitution and manipulation. I mean, a lot's going on here. You know, I went ahead and just multiplied the 1/5 times the 5, and I wrote 1. And then instead of writing e x to the fifth times x to the fourth, I switched it. I wrote x to the fourth times e to the x to the fifth. And, you know, for the most part, you know, these are simple things that I did. I multiplied a fifth times 5, and I switched by the commutative property of multiplication. But those are things that still can lose an audience. I might have even lost you for a second. They're like, well, wait, why did the x fourth go in front? That's because you're allowed. You're allowed to switch the order of things. And all of this just comes into the fluency that is really required when you do something like calculus, that you're drawing upon all the skills you ever learned in your whole life in order to just manipulate and rearrange things. Okay, I'd really like to do one more before we take a break, because I know that repetitive exposure is very important. And that way, for 10 whole minutes, your brain will be marinating in the juices of the excitement of u substitution. All right. So number 5, we have 7 over t plus 1 to the 9. And we want to integrate that. I don't know how to roll with this big. Yeah, we answer quotient, but we don't even mess with those stinking quotient rules anymore. So what's the first thing we could probably do? Yeah, we could call that 7 t plus 1 to the negative 9th a. Just for fun. Then it's not a quotient. After all, the quotient looks tricky, you know. Most of the United States is really bothered by fractions. So if we can just switch that to a non-fraction, that's good. Okay. Now, remember, we're sophisticated. And so we're looking at this saying, first of all, do you see an outside function? Do you see the outside function? Yeah. Yeah, there it is. It's something to the negative 9. And therefore, do you see the inside function? Yeah. Yeah, there it is. It's t plus 1. And is the derivative of the inside function present outside of it? So what's the derivative of t plus 1? There's 1. And is 1 present outside? It sure is. Kind of vacuously so, but it's there. So yes, this is a candidate for u substitution because there was an outside function, an inside function, and the derivative of the inside function is present outside of the outside function. Okay, so u substitution. Let u equal the inside function Therefore, du is simply equal to, what's the derivative of t? 1, so 1 dt. Now, do we have to move the 1 over to the other side? I told you to move every coefficient to the other side. Well, how about we just erase it? Because a 1 is just a 1. Who cares about 1? Okay, so we're ready for our substitution. Let's substitute everything. So remember, the outside function structure remains. The outside function structure will always still be there. And so we replace the t plus 1 with u. And we replace dt with just du. And what do we do with the 7? Well, nothing. It's just there. We could go ahead and bump it outside. Because now what we have is a simple anti-power rule. So once again, you'll notice we took something, there was a rather nasty looking quotient, and now it is simply the anti-power rule. So use substitution is pretty powerful. So let's go ahead and do the anti-power rule. So we'd add 1, divide by what we get. You'll notice that the 7 just stayed out there. A coefficient is like a good child, right? Neither seen nor heard. Isn't that what they say? Is there, no? Okay. That's a very old school 50s and before perspective on children. Okay. So now we're done. Plus c, we're going to multiply those coefficients. So that's negative 7/8 u to the negative 8 plus c. Now what could we do with that answer? Because if somebody is your friend, or your coworker, or your boss, do you walk up to them with an expression that has a negative exponent? Probably not, because most people are very uncomfortable with that, right? So instead, what would we do? We bump that u down into the denominator. So your actual answer would be negative 7 over 8 u to the 8 plus c. That's a very nice, clean answer. Yeah, how much you simplify always boils down to how much you like the person, right? Who you're giving the answer to. Like, here, you deal with it. Okay, are we right? Yeah, we are. Well, I hope. So we have to take the derivative of this. I don't want to take the derivative of this. I'm going to go back to where I was, because this is already ready to do the power rule.
Well, we never put in the.
Oh my goodness, you're right. What do we do? We have to replug the u back in. So this is actually negative 7 over 8 t plus 1 to the 8. Very good. Thank you, Josh. Plus c. And so when I check, I'm going to go back to the version that had the u in the numerator with the negative exponent. So I'm going to take the derivative of negative 7/8 t plus 1 to the negative 8. We're going to take the derivative of that to see if we get the original expression. What do you think we're going to? Can you already see what's going to happen? That we multiply the 8 out front, so it cancels with that 8, and we multiply the negative out front, cancels with that negative, becomes a positive, and then we'll have, well, okay, let's just do it. So, negative 8 out front, so I'm going to leave it there so you can do it yourself. Negative 8 times negative 7/8. Leave the inside alone. So, take the derivative, subtract 1. There we go. So you multiply by the exponent, subtract 1, leave the inside alone, and then multiply by the derivative of the inside. But what's the derivative of the inside again? Just 1. So the 8's cancel, it becomes positive, and we end up with 7 t plus 1 to the negative 9th, which, if you like the person, becomes 7 over t plus 1 to the 9th. I think in the next card I give my wife, I'm just going to write a simplified algebraic expression inside. And I'll say, it's because I like you. That'd be a good Valentine's Day card, maybe. She would understand. Okay, so did we get the same answer? We did. Okay, so really wonderful. We've done 3 examples. We'll do a couple more after the break. Conceptually, what have we done? We have expanded our toolkit of integrals that we can do into certain products that you can do sometimes on Saturdays, and only if that product is the result of a previous chain rule. And you look for that by looking for an outside function with an inside function whose derivative is also present, up to not including the coefficient. That's quite a mouthful, isn't it? It's a lot to think about. Okay, it's 11:57. Let's be back to 12:07. Hey, Henry, how do you know somebody else just never wants to do product rules ever again? They only want to do quotients. Eh?
You could make it a quotient.
For what?
You could,
Oh yeah, for integrals. Yeah, there's no quotient rule for integrals.
we can equally change products into quotients. And
Yeah.
change quotients to products.
I wonder, could we? That'd be pretty weird. I don't even know where to begin to turn a, because we don't even have an integral rule for a quotient.
Yeah.
Hmm.
Oh, yeah.
Yeah, we'll have to think about that one.
Well, if we make it, will we get lots of money?
Oh yeah, tons of money. You'll be rolling in it.
Mr. G, by
Yeah.
chance, did you upload notes to this? Because I've been taking notes, but on paper.
Wait, notes of what?
For the previous nights.
Let me look. Here, let me sit down and look. And do you need some of the previous packets?
Yes.
And here, JR, this was your previous practice test as well as test. And then, let me see here. Which sections are you looking for notes?
Chapter, section, it's 2 sections before this.
Oh, okay, so it's just sections 3.1, 3.2, 3.3.
Yes.
Do you have all those packets?
I don't
Well, here's 3.1, because I don't need it. And here's 3.2. And here's 3.3.
yeah, I think I do.
Just in case, I mean, you can have them or recycle them. And then, that's the test. All right. And when were you gonna go to the testing center tomorrow?
Tomorrow's the last day, right?
Yeah.
Yes.
Now let me see.
All right. I can use it to go today.
What's up to you? I mean, if you have until tomorrow, you might as well take until tomorrow.
Yeah.
Let me see if I can find the notes. Because I know at one time I wrote them. Hey, there we go. 3.1, 3.2, 3.3. Yes, I have notes for all 3 sections. Let me, after class, let me check my computer. I might have already scanned them in.
Okay.
But if I didn't, I'll do it right after class. All right. Oh, yeah. I'm glad you do.
You need to be regular ones and six. Regular power, not regular director.
Good question. I'm glad you asked. All right, let's do some more U substitution. So I don't know how much of all that you wrote down in terms of the verbiage, because that's quite a bit of verbiage how to think about all of this. And like I said, you can ditch all the verbiage and just try a U substitution and just start swinging it away and seeing if it works, right? That's one thing you can always do is just choose something, call it the inside function, and see if v substitution works. I have to admit that tomorrow, and by tomorrow I mean next week, we're going to learn a different strategy other than u substitution, and it's called substitution by parts. It's another strategy that allows us to take the integral of a product, a different type of product that you can do on Sundays. And in that case, there is a little bit of a guesswork. You're like, well, which one should I make the first part, and which one should I make the second part? Because when we're taking the integral of a product, if that product is the result of the chain rule, then it's easy. You look at the inside function, the outside function. But the next rule we do, you simply see two things being multiplied together, and it's not the result of the chain rule. And you arbitrarily call one of them u and one of them v. And then at that point, the question is, well, should this one be u and that one be v, or should this one be v and that one should be u? And there is a little bit of intuition you build over time, but it's also just try one. If it works, great. If not, try the other one, right? In this particular case, though, there's no trial and error. You just look for the inside function, and you're good to go. So let's go ahead and try another u substitution. Well, let's see, where do we have to go here? There's 4, 6, 7, and 9. Oh, there's actually more than that. Okay. All right, Danny. So let's go ahead and do minimum. Very good. All right. U substitution. Looking at that, which one is the outside function and which one is the inside function? What part of that is the outside function? In the square root. Recall, I just erased it, but potential outside functions look like this. Outside functions would be something to a power, or a square root, or e to the something. What do all three of these outside functions have in common? They essentially act as parentheses, or bags, that hold something inside of it. So an outside function merely needs to have some sort of a parenthesis or a container shell that something else goes inside, including an exponent. So those are all candidates for outside functions. So yes, the square root is the outside function. So everybody, let's go ahead and begin by saying, let u equal x to the 4th plus 9. So you let u equal the inside function. Or we go ahead and take the derivative. Du equals 4x cubed dx. The 9 goes away. And we immediately bring the 4 over, so we have 1/4 du equals x cubed dx. Now you'll notice I just kind of dove in. I didn't spend any time at all analyzing the function, other than just to say, there's the outside function, there's the inside function, let's try it. And so now, let's try it. We have this integral. I'm going to go over here now. I've got x cubed, I've got root 9 plus x to the 4th, and I've got a dx. And can I successfully substitute everything away? Recall, the structure of the outside function remains. And then you just start substituting things. And if it's going to work, you have to be able to substitute everything away, except for the structure of the outside function. So the 9 plus x to the 4th becomes, and then the x dx becomes, 1/4 du. So again, the x cubed and the dx, even though one's at the beginning and one's at the end, they can be replaced with 1/4 du. And again, I keep one at the beginning and one at the end. Okay, so can we take the integral of this? What are the two things we need to do to clean up? What should we do to 1/4? Take it outside. And then what should I do with my square root? Turn it into 1/2. And now, sure enough, yes, this is just a very simple integral. We can integrate it going back to our original toolkit. This is just a power function, so it's just an anti-power rule. And you go ahead and take that integral. So the anti-power rule says add 1. So 1/2 plus 1 is really 1/2 plus 2/2, which is 3/2. And then divide by what you get. What's dividing? So first of all, this is a 1 out front, right? So it's really 1 divided by 3/2. And don't forget that there's that 1/4 up front that comes along for the ride, plus c. Isn't it remarkable how many fractions come up in the process of calculus? Lots and lots of fractions. And the ability to just really quickly say, oh, 1 divided by 3/2, dividing by 3/2 is the same as multiplying by the reciprocal. So we're just going to call that 2/3. So now I have 1/4 times 2/3 times u to 3/2. And then I can cross simplify with 2 and 4, so that's 2. And I'm left with 1/6 u with 3 halves plus c. Then what? Then I go back to our original u. So we have 1/6 u is x to the 4th plus 9 with 3 halves plus c. Now, I'd say at that point that you're pretty much done. I would like to point out from advanced techniques that if you had x to the 3 halves, there's actually 3 ways that you could rewrite the power of 3 halves. You could either call that x cubed to the 1/2, which becomes x cubed square rooted, that's one option. Or it could be x to the 1/2 cubed. You see that how I split the 3 halves into 3 times a half and you might put one inside and one outside? So now this becomes the square root of x cubed. So what's better? I mean, there is no better. It's just which way would be most convenient for the end user of whoever you're giving this to. And I think that in this particular case, there doesn't matter much of anything. Other than the fact that we're about to take the integral, we're about to take the derivative of this to check our answer. And so it's best to just leave it like this, because you take the derivative using power, not a square root. So I would say that this is a perfectly fine final answer. There's no need to go further and switch it back to some sort of root. Right? You can just leave it like that. So, that said, you can all check the work later. Let's go ahead and do the next one, because I don't want to run out of time. I'm a little worried I might run out of time. I want to finish all this. So, what I'm saying is, in theory, you should all go check that now and take the derivative and make sure you get back to the original. So, how about this next one? We have an integral here, and it's x over x squared plus 2 dx. You see all these outside structures we talked about? There's another outside structure we didn't talk about yet, and that is a fraction. Exactly right. A fraction is an outside structure into which you can have something inside, either up here, or you can have something inside down here. Yeah, or both. I mean, you can only have one inside function at a time. So that's something to keep in mind. But what you might more often see is this structure. Just something over a denominator. And one reason why we're allowed to just focus on this is because I can go ahead and take this integral now and rewrite it as x times 1 over that, x plus 2. So by just separating that fraction out, just like I did a second ago, with separating out the 3 halves and the 3 times a half, I separated out x over that one fraction, and I turned it into a numerator only and a reciprocal, right? Because this is just 1 over that. So now we can clearly see the product, because remember we're working on taking integrals of products that you can do on Saturday. And now for sure what I have is a outside function called a unit fraction. Anytime you have a 1 over a number, you call it a unit fraction, because number 1 is considered a unit and this is a fraction. So given all that, what's our inside function? Yeah, x squared plus 2. Took a little bit of rewriting, didn't it? Yeah, took a little bit of rewriting to kind of see that, because you might have said, well, is x the inside function? But just consider, let's say that you had said, hey, let's let x be the inside function. Then you'd have said, let u equal x, and then you'd have du equals dx, and then you'd have gone to substitute everything, and you'd have substituted it all to become u over u squared plus 2 du. And you'd have looked at that and said, is that any better? It's the exact same thing, it's just in the u variable instead of the x variable. So you'll notice that was a non-starter, right? That was the wrong choice for the inside function, because it didn't help. So now you say, okay, no, better not do that as the inside function. Let's let u equal x squared plus 2. So we say, let u equal x squared plus 2, and therefore du is equal to 2x dx, and you move over the 2, you get 1/2 du x dx. And most importantly, you'll notice the inside function is the derivative of the inside function present, not including the coefficient? Yeah, the derivative of x squared is 2x, and x is present, not including the coefficient. So this does fit the overall idea of chain rule. So now we can do our u substitution. So the outside function, remember, the outside function, the structure of the outside function always remains. So now we just substitute in the u, and then x dx becomes 1/2 into u. I hope that everybody in the room is seeing that clear visual that x dx is the same as 1/2 du. And that you're literally substituting x for 1/2, substituting dx for du. Okay, so now x becomes 1/2, and dx becomes du. And now we bring out the 1/2, just to clear it up, and this is 1 over u. Well, ooh la la, that is yet another simple integral from our original integral toolkit. Notice, for a split second there, I was about to bump that u into the numerator. What would have happened if I had bumped that u into the numerator and I said, hey, let's do the integral this way? What would have happened? Add 1, divide by what you get. Add 1, divide by what you get. It would have been undefined. And I would have been like, oh, wait. That's the one special case. The integral of 1 over x is really the natural log of x. Okay, so now we do the integral. So that'd be 1/2. And the natural log of u plus c. I like u substitution too because it opens you up for like lots of like elementary school jokes like u substitution. No, u substitution. No, not funny. Or like you say things like the natural log of u. What does that even mean? All right. So what's the final step? We're all done with the integral. We replace the u back with the original substitution, which is x squared plus 2. Now are we done? I mean, we're done doing the integral. We have no idea if we're right or wrong. We could be massively and wildly wrong. So we would check. And this one is a little tricky, so let's check it together. When you check the derivative of natural log, it's been a while since we've done the derivative of natural log. So let's take the derivative of 1/2 natural log of x squared plus 2. So when you take that derivative, remember the 1/2 coefficient just comes along for the ride. And what's the rule for taking the natural log? The derivative of natural log is 1 over the argument. Yeah, very good. That's the right way to say it. 1 over the argument. So the derivative of natural log x squared plus 2 is 1 over the argument. And then this is technically a chain rule because there's an inside function inside the natural log. So you take the derivative of the outside function, which is 1 over the argument, leave the inside alone, and then multiply by the derivative of the inside function, which is 2x. So that's the derivative of 1/2 natural log of x squared plus 2. And how does that clean up? What cancels? Yeah, the 2 and the 1/2 cancel out. And then the x, can we just go ahead and bump the x into the numerator of the fraction? Because that's really x over 1, so we can multiply the fractions, and we get x over x squared plus 2. And is that the original integral? Yeah. So we got it. Did anyone else think of any other outside structures? I mean, if we were, oh, well, hey, we just did one. That's another outside structure. If we were doing trigonometry and such, I suppose you could also say trigonometry. We have an inside function. And in fact, then, what are really all of these things? What is an outside structure simply? Yeah, they're all just functions, right? They're all just functions. So the minute you write down a function like f of x equals, a parabola, x squared, the minute you write it empty, the minute you write any function empty, it automatically is the structure of an outside function into which you can plug something in. So really the outside is any function. In fact, you can even just write that, f. Then that would be the outside structure, and the inside would be whatever you write. Yeah, any function at all. Okay, how's everybody feeling? Any particular questions? This is it for the day, is U substitution. U substitution is a technique that we use frequently, and that it takes some getting used to, like pulling yourself across the room on a chair. Okay, you practice a little bit. All right, let's do the next one. What makes number 7 a little different? Yeah, well, it's a definite integral, so we actually will find some area. So before we even do that, let's find the area. I always like to know the answer before I start. Why not? So we're going to do the integral from 0 to 3. There we go. So 1 over 5x plus 5, that's what we're looking at. And we're going from 0 to 3. How much area is there between 0 and 3? Yeah, not much. And from my perspective, doesn't seem like a lot. So now if I actually take that integral, from 0 to 3, 1 over. There, it's only 0.277. So just over a quarter. So we can keep that in mind now as we do the integral. So everybody, as you rewrite that in your own handwriting, really emphasize the outside structure. Well, first of all, where does the dx go? There, it goes all the way on the end, right? That was kind of weird that they put it in the numerator. What's actually in the numerator? Now 1. Okay, so now, there. So just writing at that so far, does everyone see the outside structure? Yeah, and then you can go ahead and write in your inside structure. And we have no coefficients or anything to mess around with. And we're going to keep track of that 0 to 3 through the whole problem so that we can eventually do the fundamental theorem of calculus and plug it in. So everybody go ahead and try U substitution. So everyone started with U equals 5x plus 5. Yes, you need both of those. Those are fundamental. And then we're that's it. So we all started with U equals 5x plus 5, and then we all had du equals 5 dx. And then what did you have to do with 5? Pump it over to the other side is 1/5. So just comparing notes that far, we would all have that u equals 5x plus 5. So du equals 5 dx. And then 1/5 du equals dx. And then you can start doing all your replacements. You'll notice this time when you do the replacement, the 1/5 isn't replacing anything in particular, is it? The 1/5 we're just going to go ahead and insert into the integral where? Since u goes into the bottom and du goes at the end, where do we put the 1/5? Sure, you can put it in place of the 1. You could put it in front, or eventually we're just going to pull it outside, so you can take it outside. I pretty much always, as a rule, put my coefficient in front of the thing and then the du at the end. But as Josh did, you can also put the 1/5 on top instead of the 1. Because, yeah, in a moment, I'm just going to go ahead and pull that 1/5 out front. So I'm just looking at 1 over u here. Because then that's a nice simple integral from our toolkit. So what is the integral of 1 over u? Yeah, the natural log. So now I have 1/5 natural log of u. And it's not a, do I write plus c? I don't actually write plus c this time. There's no plus c because we're actually going to do the evaluation from 0 to 3. So fundamental theorem of calculus says you write out the structure twice, and then plug in the top number, plug in the bottom number, and subtract. So, but what do we do before we do it? Yeah, replace the u. Because remember, u is just a dummy variable. Do you know that's actually what it's called? When you use substitution, it's called a dummy variable. Isn't that interesting? U is a dummy variable. See, once again, that sounds like such a good insult. You're like, u is a dummy variable. Like, it's just so silly. And yet, that is what we call it. That's the technical term. U is a dummy variable. So, that is not, if you plug in the 3 and the 0 right now, it would actually be a big problem. If you did something minus something, and it was 1/5 natural log of something minus 1/5 natural log of something, if you plugged in 3 and 0, what's the natural log of 0? What? What is it? Natural log of 0? Just type it in your calculator. What is it? Anyone typed it in? What? Error. It's undefined. Yeah, that's undefined. So if you ever forget to substitute back u into your original variable, you'd hit it undefined. And I cannot tell you the number of times I've done this. Where I'm like plowing along super fast and I forget to substitute back into my u variable and I hit there and I'm like, ah, what happened? And then I'm like, oh, I have to rewrite this out as 1/5 natural log of 5x plus 5 from 0 to 3. Now that's going to work. That would not be undefined. Okay, so that's our structure. So we do the fundamental theorem of calculus, which is something minus something, where we use the structure 1/5 natural log 5 something plus 5, and 1/5 natural log 5 something plus 5. You'll notice I'm a real big fan of writing in the entire structure first, before I drop in the number 3 and 0. And for me, it's just very robotic. You know, I write the structure, then I plug in the numbers. And I think it helps me, especially in terms of using my calculator now. So in my calculator, I write the structure. So my structure would be 1/5 times natural log, parenthesis, 5 parenthesis, 3 parenthesis, plus 5 parenthesis, and that gives me the first part. 1, 6, 7 minus the second part. I just go back and I plug in 0. 1, 3, 2, 1. And that gives me, and see now my calculator has all those infinitely many decimals. So, no, I think I still have to type them all. And did anyone else get 0.27725 Is that right? That's what Desmo said. Desmo said 0.277. It's just over a quarter. So what would Moore want? Moore would want 4 decimals. So the actual answer would be 0.2773. And that would be the answer that Moore would accept. Questions, thoughts? Emotions? Feelings? Whimsies? All right. Number 9, I think we've already done a problem like that. Did we do? Yeah, we did. Number 3 is just like number 9. So we're going to skip number 9. Not skip it, you can do it on your own. But we're not going to do it together. And now let's consider, last section. We're going to look at the antiderivative of e to the something, which is really quite great. You're all going to be able to figure it out. Too sweet. So consider the antiderivative of e to the nx. And before we even attempt this, let's consider what's the derivative of e to the nx. Who remembers what's the derivative of e to the nx? There's just n e to the nx, right? Because that's the chain rule. So the derivative of e to the x of e to the anything is e to the anything, and then we multiply by the derivative of the inside, and the derivative of nx is n. So there we go. So if the derivative of e to the nx is e to the x times n, the integral of e to the nx is e to the nx divided by that. And you'll notice that looks very, very similar to the power rule, right? I know we've already talked about this. It was a few days ago, though. So the derivative of x to the n is n x to the n minus 1, and the integral of x to the n is 1 over n plus 1, x to the n plus 1. So there's some similarities here, and there's some dissimilarities. And that's what makes it so tricky, because our brains start to remember both simultaneously, and then we start writing down crazy things like 1 over n plus 1 e to the n minus 1 x. Like, can you just imagine how confused it gets in your brain as you try to remember what was that rule? So this one is well worth writing down. Then the derivative of e to the nx is just multiplied by n. The integral of e to the nx is just divided by n. Now that's all, hot and dandy that we just wrote that down. And, we use this idea that, like, well, derivative and integral are opposites. So if here I multiply by n, here I divide by n, how far does that kind of logic really take us in mathematics? Sometimes it works, sometimes it doesn't work. So what would we really have to do? We should actually do the integral. So let's try it. Let's actually do this integral. The first problem is we don't know how. Because we don't have a formula for it. So what would we do? Do you see an outside function? Do you see an inside function? What's our inside function? U equals nx. So let's run with it. Our outside function is e to the, our inside function is nx. So now du equals n dx. Bump the n to the other side, so that's 1 over n du equals dx. Does all that seem fair so far? Now this almost seems like downright cheating at cards. Like, we admit we don't know how to do this derivative, so we do u substitution. And when you do, what do we end up with? E to the u, and dx gets replaced with du, and there's a 1 over n out front, which, if you'll notice, what did we end up with in the formula, the 1 over n? So now we bump that 1 over n out front, and we're just taking the integral of e to the u. And that is a function that we can take the integral of. It's simple. So now we say that the derivative is 1 over n, the integral is just e to the u. Let's see. And now we're at 1 over n e to the u, and the last thing we always do is substitute back with u, and we get 1 over n e to the nx. Let's see. Yeah, it seems like so much smoke and mirrors, because we get to the answer that we expected anyway. Anyway, but at least we did it legitimately. Like, that was not cheating. That was genuine u substitution telling us that the integral is 1 over n e to the nx. Now, what I'd like us all to do now, then, is add that to our toolkit. I mean, we already wrote it down once, but we should now consider e to the nx as part of our toolkit. We should not consider doing u substitution every time you see e to the nx. So, for instance, the very next couple of problems they give us after you turn the page, they give us a whole bunch of e to the n x problems to take the integral of. And these are in the u substitution unit. And that's because you would technically solve it using u substitution. But we, being sophisticated calculusticians, are we going to do u substitution to solve these, or are we just going to use that formula from our toolkit? I'd say we can just use the formula from the toolkit. Now, if you really wanted to, you could do the whole thing using u substitution. But for once, I'm suggesting that you don't have to do that extra work. So what would we do here then, folks? The integral is 3e to the negative 5x. Let's go and bring the 3 out. So we just have e to the negative 5x dx. That's our integral. Sarah, this one's on the next page. Oh, you're still doing, okay, that's fine, sorry. I just want to make sure you did. Okay, so how does the rule work? The integral of e to the nx is just e to the negative 5x, and you, like that. You divide by the value of that. And so we're done. So you multiply the fractions together, that's negative 3/5 e to the negative 5x. Plus. How's that? And everybody can go ahead and do number 11 as well. You can do 11, and you can do 12, and you can do 13. But 12 and 13 are both definite. We'll check back in again. So everybody finish up 10 and 11. Yeah, which is we divide by 110, multiply by 10. Yeah, that's it. Yeah, when you divide by very nice. I'll put the hands up here so you can all check your work. Well, first, you don't even have to take out the 130. I know I keep on role modeling taking the coefficient out, but maybe it's easier not to take the coefficient out because then the 130 becomes the thing that you're dividing by 0.1. And you just have 130 divided by 0.1 equals 0.1x. And that's your answer because you're just dividing by the coefficient on x. And then dividing by 0.1 is 1300, is timesing by 10. There we go. This is a good integral to know, e to the nx, because believe it or not, there are actually lots of application problems in which you need to do an integral of e to the nx. Actual business applications with money and investing that we're going to see within the next couple chapters. That said, these next two problems, 12 and 13, are just good problems to warm you up on doing that calculation so that later on when we throw in money and investing, it's just a matter of routine course to do that calculation. All right. So, this is a definite integral. I don't know about you, but before I do it, I would like to know what the answer is. So I can have that nice immediate feedback that I did it correctly. There we go. So we're going to do E to the 5x, and we're going from 0 to 1. Now, look how quickly that function goes up. It goes up awfully fast, so I need to change my window so I can see this better. We go from -1 to 2, and we go from 10 to 1,000. Yeah, there we go. There. Now we can actually see it. So we're going from 0 to 1, right? And how high does that go? 1. If you were to make a triangle out of this, what would you say your guess is? So notice that's 1,150 units tall. It kind of looks like a triangle, but not a very good triangle, huh? No, because if it was a real triangle, it would be, that's, what was that? 1,150. That's the one. If I wanted to draw a line from the origin to there, wouldn't it just be a line, mx plus b, where the slope is up 1,000? Well, that's the x value. Oh, it's only 148. Oh, how embarrassing. I misread that coordinate. There we go. So if I call this thing a triangle, would I be right?
No.
No. No, terrible. In fact, how much of my shape it takes, how much of my shape is filling in the actual triangle? Maybe only like half. So if I were to try to use a triangle to approximate that, I wouldn't just use the triangle area formula 1/2 base times height. What would I do? Yeah, 1/2 base times height. So my base, so that's 1/4, my base was 1 and my height was 150. So let's just say that I'm thinking the answer should be around 150/4, which is 7/2, which is 37.5. So I'm going to say the answer should be 37.5. Right? Now, why do I do all this? You know, like, all right, first we're going to graph it to come up with an approximation to what I think the answer is, and then I'm going to actually do the integral and find out what the answer is. And ultimately, you know, what is it that I'm doing? I guess I'm just kind of playing, you know, because that's what we do sometimes is we play. So the answer is 29.4. Oh, my approximation was pretty bad, wasn't it? So my curvy shape thing was less than 1/2. So the answer should be 29.48. Okay. We can finish these last two problems. All right. So what was it? 29.48? Oh, so sad. In the past, my approximations have been pretty good. That one was a little off. All right. I'm just going to do it down here so you're standing on the chair. So we're going to go from 0 to 1, e to the 5x dx. And so the integral is simply 1/5 e to the 5x from 0 to 1. And so by the fundamental theorem of calculus, it's parenthesis minus parenthesis. And so that'd be the structure, 1/5 e to the something. Well, e to the 5 times something. And then the structure is 1/5 e to the 5 times something. And something that we're plugging in is 1 and 0. I like plugging 0 into functions, don't you? That'd be like something you say when you meet someone for the first time, you're on the first date, and you're like, what are you into? Like, plugging 0 into functions. What do you think? Does that take you far? I think so. So that's 1/5 e to the 5th minus 1/5 e to the 0 is 1. So there we go. Now, just in terms of, again, how much you like the person you're giving your answer to, you could leave it like that, or you could factor out the 1/5, and it'd be e to the 5th minus 1. You know, maybe that has a certain visual appeal. I don't know. In any case, let's see if our decimal answer is what we expected. E to the 5th minus 1 over 5. Yep, 29.48. In terms of desmos, you would need 4 decimals. So that's 29.486. There we go. Okay. I know we have 2 more problems. I think I'll just do the next one, and then we'll be done, and we'll save the next one for the next time. How does this problem change now that there's a 340 there? Not really much of anything. In fact, it's kind of nice that the 340 is there because it gives us a number to divide by 0.03. So when we do this one, it's just going to become 340 over the 0.03 e to the 0.03x. And we're evaluating that from 0 to 4. I like plugging 0 in the functions. How about you? All right, so then 340 divided by 0.03, what is that? Now, oftentimes when we do these problems, it's going to be a repeating decimal like that. So you can write it out as 11333.3 repeating. That's a perfectly legitimate way to write something. You just use the repeating bar. And then e to the 0.03 x from 0 to 4. So then again, your structure would be 11333.3 e to 0.03 something, and 1 e to 0.03 something. And that something, the second time something. Actually, it's a 4 and that's a 0. Folks, can we be smarter about this? Like, that was kind of a bummer to write out that number twice, wasn't it? You could do this fraction. What else can we do to do even less work? So this bar here is telling us to take this structure and subtract. You'll notice that the 11333 is part of both of these, so we could have factored it out. In fact, what we could have done is left the 11333.3 repeating outside of the e to the 0.03x from 0 to 4. Because then all we would really do is have the 11333.3 repeating outside of the structure minus the structure. And that's something we haven't done before, so I thought that'd be worth saying. That a coefficient can stay outside of the fundamental theorem of calculus. So now we just do e to the 0.03 times 4 minus e to the 0.03 times 0. So then that just gives us e to the 0.12 times 1. So that would be an exact answer. And then you would get a decimal approximation, e to 0.12 minus 1 times. Now when you type in 11333.3, how many point threes do you get? At least a whole row. Like, all the way across. You might say, you're crazy. For so many reasons. But you know, that way you at least know that whatever answer you get, how many decimals of accuracy do you need? 4. So whatever you do in your previous calculations, if you want to end up with 4 decimals of accuracy, you should have at least 8 decimals going into your calculation, right? Like double that, just to be safe. But a whole row is going to be more than safe enough. So 1444.964, and that's 4 decimals of accuracy. All right, super dandy, folks. We did all but that last problem, which, to be fair, and that is a fun one. So we can just wait to do that one together. You can always go home and look at it if you like. You don't have to. I know you all want to stay. Do you think if at the beginning of the year I had told you that there was a mix-up in scheduling and our class actually goes until 12:20? Would you believe me and would you have stayed, or would you have gone to registration and actually verified my claim? I wonder. I wonder how much I could have gotten away with. I'll have to try that next semester. Just start lying to my classes and telling them that the class goes longer. I'm trying to give you free education. That's not the worst thing I could do to you. I could be pickpocketing your backpacks while you're studying. That wouldn't be nice at all. See you. See ya. Sarah, did you see your AZ merits last week? Oh, no, you're a senior, you don't work there. Oh, there we go. Oh, this week. But I bet you missed it though, huh? You're like, oh man, I wish I could have taken the AZ merits. What do you want? Oh, you're showing me the other one. Okay. And what? Oh, you hate this ISS? I see. Why?